Hi, today we're going to solve a polynomial equation, but we're going to do so by using perturbation theory. Normally when we solve polynomial equations, what we think of doing is using methods like factoring, or maybe using a quadratic formula, a cubic formula. But in our case, we have the equation x to the power 7 plus x equals 1. Now we want real valued solutions of x for this equation, but the problem is, if we try to rearrange this, take all terms to one side and factor, setting equal to 0, we won't be able to do that. Moreover, we have no safety net like the quadratic formula to fall back on, because beyond quartics, there is no formula that can help us solve polynomial equations. So how will we tackle this? Well, this is why we're going to try to use perturbation theory. So what is perturbation theory all about? Well, there's a couple of steps involved when we use perturbation theory to solve equations. The first step is to take what we have and try to solve a simpler version of that question. So for us, in this equation, what might be simpler? Well, we could neglect this term here and have x to the power 7 equals 1 and solve that. Or we can neglect this term here and have the equation x equals 1 and solve that. Well, the choice in what to do exactly is a little bit subtle and requires a little bit of finesse. But for the purposes of this exercise, we're just going to say that we're going to cover up this term and simplify our problem to begin with by solving x to the power 7 equals 1. So let's consider such an equation. But this equation came about how? It came about by taking what we have, and it's like we multiplied this term by a number 0. Let's call that number epsilon. This is the perturbation parameter. So with epsilon being 0, that reduced our problem to this one here in blue. Now solving that one in blue simply gives x equals 1. That's the only real solution to that equation. Okay, well that's fine, but it's not exactly this equation we want to solve, right? It's this equation. So looking at what we've done over here, we simplified our original question by introducing this perturbative parameter epsilon, made it 0, and looked to see what the solution was in that simple case of x to the power 7 equals 1. But really, we need epsilon to be 1, because then that will be representative of our actual question. If this was 1, then our two equations would match. Okay, well ultimately that's what we want to do then. But how is exactly introducing this perturbation parameter of any help to us? It's like we're maybe making this more complicated by introducing more into the question. Well, in fact, this is going to be more helpful. What we do first of all is assume that the solution to this equation, so the values of x that satisfy this equation, are actually functions of epsilon. So assume the following, that our solution for x is a function of epsilon. But the solution that we get, we also assume that it's kind of like a power series, or it's Taylor-like. So assuming that, that means our solution will look like x of epsilon equals the sum from k equals 0 to infinity of a sub k times epsilon to the power k. Well, let's expand this out a little bit and look at a few terms. Our solution to the equation x of epsilon is nothing more than a sub 0 epsilon to the 0 plus a sub 1 epsilon to the 1 plus a sub 2 epsilon squared plus a sub 3 epsilon cubed, and so on. So this is what we're going to assume that our solution is for x as a function of epsilon for this equation. But for this equation, when epsilon is 0, so this term is gone, we have x to the power 7 equals 1. But we know the solution to that equation is x equals 1. So when epsilon is 0, the solution is 1. So this series sums to 1. So that gives us the following. First of all, epsilon to the power 0 is just 1. So we have a naught plus a1 times epsilon to the 1, but epsilon is 0, plus a2 times epsilon squared, but epsilon is 0, plus a3 times epsilon cubed, but epsilon is 0, and so on. So all these terms here beyond a naught are all 0. So what we find off the bat is that a naught equals 1. The first term of this series solution is 1. Okay, well, if this series is supposed to be the solution to our equation, then we could sub that series in here for x, here and here, expand it out, and solve. Let's make our job a little easier. Let's take our solution here and write it as the following. A naught, which is 1, plus a1 epsilon, plus a2 epsilon squared, plus a3 epsilon cubed, and so on. But what we're going to do is call this part of the sum, the part of the sum that contains the epsilons, we're going to call that S. By doing that, we now have x of epsilon equals 1 plus S. So if this is our solution to this equation, then 1 plus S should satisfy this. Let's plug in 1 plus S into here and here for x. So that gives us the following. X to the power 7 plus epsilon times x, so times 1 plus s, equals 1. All right, well now we have this binomial raised to the power 7. So we might think of Pascal's triangle perhaps to expand that out. And when we do that, the first few coefficients are 1, 7, 21, 35, etc. So expanding this out, we get 1 times this to the power 7, this to the power 0, so that's just 1, plus 7 times, that's the next entry in Pascal's triangle, this to the power 6, this to the power 1. So these exponents are dropping by 1, these are rising by 1. Plus the next entry in Pascal's triangle, 21, times this to the power 5, this to the power 2. And we'll just stop there, actually. If we go all the way, we're going to have a lot of expansion to do. We'll be here all day. But up to here should give us enough that we can come up with a pretty good approximation for our solution. So stopping there, we then have plus epsilon times s equals 1. Well, now we know what s is. S is this series here, a1 epsilon plus a2 epsilon squared plus a3 epsilon cubed plus 21 times this again, a1 epsilon plus a2 epsilon squared plus a3 epsilon cubed and so on, and that's squared, plus epsilon times s. Again, here's S. And that equals 1. Okay, perfect. Well, this is easy to distribute. This is easy to distribute. But we're going to have to square this bracket before we go any further. So let's do what we can first easily. We have 1 plus, okay, 7 distributed into this bracket. So 7a1 epsilon plus 7a2 epsilon squared plus 7a3 epsilon cubed, and that would keep going. Plus this epsilon down here. Plus now we distribute this epsilon into this bracket. So we get a1 epsilon squared plus a2 epsilon cubed plus a3 epsilon to the power 4. Now again, we're going to actually stop at powers of 3 for epsilon, because in the expansion over here, having 4 terms will give us a pretty accurate answer. So we're not going to go beyond powers of 3 on epsilon. So we'll just stop there and leave that term out. Of course, that makes our accuracy suffer a little bit, but not much. And same thing here now. We have to square this bracket, and of course we're going to get higher powers than 4 there. We're going to have epsilons to the 4, 5, 6, but we'll only go up to epsilon cubes. So what does that give us? Plus 21 times, well, how do we square this? We're going to take this term and distribute it to itself, this, and this. And then take this term and distribute it to this, this, and this. Then we'll take this term and distribute it to this, this, and this. And that gives us the following. a1 squared epsilon squared plus a1, a2 epsilon cubed. And we'll stop at that power of epsilon. So we'll move on to the next term. Plus a1, a2 epsilon cubed. Again, that's good enough. We'll stop there. Distributing this gives us an epsilon to the power 4, so we won't even bother. So we'll stop it there. Okay, good. So now let's just distribute this 21 into the bracket and see what we end up with. Although before we do that, we have a1, a2 epsilon cubed and a1, a2 epsilon cubed. This and this give 2 a1, a2 epsilon cubes. All right. So where are we at now? 1 plus this plus 7a2 epsilon squared, 7a3 epsilon cubed epsilon, plus epsilon, plus a1 epsilon squared, plus a2 epsilon cubed, plus 21 a1 squared epsilon squared, plus 42 a1 a2 epsilon cubed, plus. So now let's gather all like powers of epsilon. So for example, we have powers of epsilon cubed. What are those terms? We have a 7a3 factors out. We have an a2. And we have a 42 a1, a2. Then let's look at powers of epsilon squared. Well, we have 7a2 factors out, 21 a1 squared factors out, and that's it. Oh, and plus an a1. And then powers of just epsilon. Well, for there we have 7a1 plus 1. Then we still have this constant here, 1 on the left side, equals 1 on the right side. Well, since this is a function of epsilon, the coefficients here of epsilon cubed, and the coefficient here for epsilon squared, and the coefficient here for epsilon, they have to match the coefficients on the right side for epsilon. But on the right side of the equation, the coefficient for epsilon is 0, And same for epsilon squared and epsilon cubed. So that tells us that this sum is 0, this sum is 0, and this sum is 0. Well, having said that, if 7a1 plus 1 equals 0, that just tells us that a1 is negative 1/7. And taking that solution and now plugging it in here and here, we can solve for a2. And if we do that, a2 turns out to be 2 over 49, negative. And then that gives us, there should be a 42. That gives us for a3, negative 10 over 343. So we can sub in a2 here and here, sub in a1 over here. So we know all this, and we can solve for a3. But now that we've done that, we've found the coefficients of our series representation for the solution to our equation over here. Recall, x of epsilon is just this right here. So x of epsilon is 1 plus a1 epsilon, that's negative 1/7 epsilon, plus a2 epsilon squared, so minus 2 over 49 epsilon squared, plus a3 epsilon cubed, so this times epsilon cubed. Well, there we have it. There's our series representation for the solution of our equation here. But remember, we want epsilon to be 1 because then this perturbed equation matches the equation we're trying to solve from the beginning. So with epsilon equal to 1, we therefore have x of 1 equals 1 minus 1/7 times epsilon, which is 1, minus 2 over 49 times epsilon squared, that's 1, minus 10 over 343 times epsilon cubed, that's 1. Well, what's 1 minus 1/7 minus 2 over 49 minus 10 over 343? That gives us 0.787 approximately. And what is the solution then to this equation if we were to use a calculator? Let's compare. If we compare, the solution via calculator gives us x is approximately 0.797. So from an originally pretty intractable problem where we couldn't factor, we couldn't use any sort of formula like the quadratic formula, we introduced this perturbation parameter here to help us find an approximate solution. And that's not so bad. Now, if we take more and more terms, had we expanded this further and kept more terms, had we kept more terms here and here, and looked at a much longer series with more terms, then of course this answer would have come much closer to this. But with just a few terms, we're actually already pretty close. That's quite close. That's very good. So there we have it. We've solved this polynomial equation, this septic equation, through perturbation theory. I hope you enjoyed.